I want to talk about keyboard scanning today, and if we have a little bit more time to start talking about direct digital synthesis. Let me remind you that Wednesday afternoons there is no lab section, but the lab is open. So if you want a couple extra hours to work on a project, feel free to stop in, or you got some questions about the course, stop in. I'll be there all afternoon, and every Wednesday afternoon. Also Thursday and Friday, but Thursday and Friday there's classes, so I'm a little busier. Any questions so far about Lab 1?
Lab 1 about the natural 1.2 reference voltage. Yesterday we are measuring the charging and discharging plots. I think can we add one line of code to when the comparator catch when the input the input capture the signal, then it sets the charging point to output and turn to 0. So the plot will have a big point at the real reference voltage. If we are only charged to 1.2.
Okay, why do you want to do that?
We'll collaborate the reference voltage.
How does that calibrate it?
Yeah, because if we turn the output to...
Oh, I see what you're saying. I see what you're saying. So, so when the capture occurs, turn off the output, and that will tell you the yeah, that'll work. Now, I would guess that most people's measurement of the threshold voltage for the comparator is probably only good to 1% or 2%, because the oscilloscope is only good to 1% or 2%. It reads 3 digits, but it's not. That third digit is highly suspect. So consider carefully alternate ways of calibrating. One way is to use a good capacitor. What is a good capacitor? A good capacitor is a capacitor that has minimal dielectric absorption. Remember what dielectric absorption is? This is an obscure question. Dielectric absorption is a nonlinear effect of charge where the dielectric actually takes up charge. And depending on the method by which the capacitance is measured, the dielectric absorption will be different. And I've seen some of the cheaper capacitors in the lab, some that are about the same age as me, where the capacitance read by the commercial digital voltmeter and the capacitance read by the student circuit was 20% different. But the capacitance for a Mylar capacitor was the same. So the cheap ceramic capacitors you cannot necessarily trust to measure the same on the voltmeter as it will in your circuit. So you might want to look for a Mylar test capacitor for calibration. Or at least not an X7R ceramic. There's usually 2 numbers printed on a capacitor. One is like 203. 203 means 20 times 10 to the third picofarads. So it's 20,000 picofarads, which is 20 nanofarads. And someplace else will be the chemistry or the dielectric often of the capacitor, and it will say something like X7R on it, which is a very inexpensive but fast dielectric. Watch out for dielectric absorption. Any other questions about Lab 1? The spec says the accuracy should be within the accuracy of the resistors you use for the circuit. we're using 5% resistors. The TAs are going to test at 1, 20, and 100 nanofarads. Anything else on lab 1? Yes? Louder. Dead on. No, they know within a few percent. Also, they're going to use the same capacitors for everybody. And so if there's a systematic error across everybody, I think we can all figure out, maybe the capacitance is wrong, not the circuit. Let's go back to lab 2, keyboard scanning. Last lecture, seems like a long time ago, last Friday, gave a schematic for the keypad we're going to be using, which is an array of 12 switches. Each switch connects one column wire with one row wire. The way I set it up, you don't have to set it up this way, but the way I set it up, I drove A0 through A3 as output lines from the microcontroller with a 300 ohm resistor on each one of the lines. That's to avoid shorting two of the pins together if the silly user presses, say, pins 4 and 7 simultaneously. And 10K pull down resistors on the B7 through B9 ports. But then I figured out how to turn, with Tamid's help, figured out how to turn on the pull down resistors, which I think I said last time. Yeah, I'm pretty sure I did. So, are there any questions about this? We have enough keypads in the lab. Each group can take a keypad and keep it for the semester. Don't have to swap out keypads. A couple of things about the keypads. The new ones, the ones I just bought, have 4 little mounting studs on the bottom. They're meant to press fit through an aluminum panel or a plastic panel. And I strongly suggest that you snap off 2 of them. You snap off the 2 in this corner, but you leave the 2 in this corner, in these corners, because that way the keypad has something to rest on. So if you cut off all 4, then when you press down here, it's going to push this right out of the whiteboard. So, how are we going to scan this thing? What we're going to do is we're going to sequentially. Can you see that with the weird backlighting? Is that okay? So on row 1, that would be A0. We're going to put out a pulse. Then sometime later, we're going to put out a pulse on A1, then A3, then A4. Sorry, A2 and A3. So we're going to scan the line by setting each row high for a short amount of time. And during that time, let me put that back up at the top so you can see it. Then at each one of these points, we're going to read B7 through B9. Then Then we're going to concatenate the bits. So we're going to OR together the bit pattern for the drive, which in this case would be 0x01, 0x02, 0x04, and 0x08. We're going to concatenate this with the possible bit patterns for B7 through B9. So for instance, if you pushed button 0 and we ORed together A1, A0 through A3 with B7 through B9, we would get 0x, well, let's see, bits 7 through 9. Let's see, that's bit 8 is hexadecimal 100, right? So bit 8 is hexadecimal 100. So we're going to OR together B8, and row 3 is A3, which is 0x08. So when we OR those together, we're going to get 0x108. So 0x108 is going to be the scan code for button 0. Corresponds to the line which is high at the time you read port B. So the line which is high, B7 through B9 are going to be all 0 when we bring A0 high. They're going to be all 0 when you bring A1 high. They're going to be all 0 when you bring A2 high, because none of those are connected if you press button 0. When A3 goes high, suddenly B8 will be set. We can detect a non-zero B value and OR together the A value with the B value to make the scan code. So what's going to be the scan code for button 1? Button 1. What's the scan code? That means when A0 goes high, the A port, A0 through AC, A0 through AC, A3 will have value 1. And if button 1 is pressed, then bit B7 will be high when that A line is high, correct? So the scan code will be? Say again? 10. No, that's the code for that. That's B8. That's the 8th bit.
Right.
So B7 would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 to the 0, 2 to the 1, 2 to the 2. 1, 2, 4, 8, 16, 32, 64, 128, 256. 256 is hexadecimal 0x100. Hex digits. So, what will be the scan code? B7 is high. What is the value of bit 7? Don't remember hexadecimal. So sad. 0x80. Exactly. So it's going to be the 8 here because bit 7 has a value of hexadecimal 80, and it is, and it's bit, and the low order bits are set by A, which is 1. Okay, what's 5? Very good. 0x102. It's the second row down. Second row down. So the O2 is set, and B8 is set, so it must be, the high order digits must be hexadecimal 100. So we're going to wait. We're going to scan the keypad until we get a non-zero B result. Scan the keypad until we get a non-zero B result, and OR together A and B ports. And that'll be the scan code. The next step will be to be a table lookup to convert that to something useful like a digit number. Okay, let's look at the scan code. There's a bunch of random threads here I won't bother to look at. But the documentation for the keypad thread is here. In your code, you are going to have to use this keypad thread as a scan thread, which you will call about 40 times a second or 30 times a second. So what we're going to do now is we're going to have a table lookup. Well, let me first let's talk about the scan process to make it, to go over it again. We're going to clear all the bits 0 through 3, set the pattern to unity, and then set the port A bits to pattern. That sets A0 through A3 to 1, 0x1. We're going to hit this about every 30 milliseconds, which is about right. And then we're going to read keypad as bits 7 through 9 on port B. We're going to see if it's 0. If it's not 0, then we're going to OR the keypad output with the pattern input. That is to say, we're going to OR the 3 B bits with the 4 A bits. And then break, which kills the for loop. So the first time we get a match, we're done. If we don't get a match, we clear the current pattern in the A bits, we shift it right, left by 1, and then we set the new pattern back onto the A bits, go through the loop again. So that's the scan process. After that, we're going to search for the key code. If keypad is greater than 0, that is to say, if something is pressed, then we're going to search a table based on keypad to see which digit was pressed. Now we can go back up and look at the table, which hopefully now will make some sense. So key table is arranged so that entry index 0 is the scan code for 0. Entry 1 is the scan code for 1. Up through 9. And then the top 2 scan codes are for star and hash. So then what comes out of this table search is either a digit organized by the value of the digit, or -1 if nothing is pushed. So let's ask what happens under some error conditions. What if the foolish user, and they all are, presses 2 buttons in the same row? Let's say fat finger hits 1 and 2 at the same time. What happens to the process?
It's got a for loop. It's going to hit the 1 first and use that.
It's going to hit since we have a for loop, it's going to, when A0 is high, it's going to notice that B is non-zero and drop out of the loop with that scan code. That is correct. And the scan code will be 7 and 8, so that's hexadecimal 181, which isn't in the table. And so you will return a -1. So if you press 2 in the same row, you get a -1 saying that there is no valid key push. So -1 can mean either no key push or no valid key push. What happens if you press 2 in adjacent rows? This is a little harder to understand. It worked, but not for a logical reason. It worked for an electronic reason. It'll return -1. Why? Exactly. You hook pin 1 and 4 together. The node values are less than the CMOS threshold. It never detects a 1, and you get all zeros out. So it rejects electrically the case where any 2 buttons are pressed vertically. If you replace these with diodes, you would be electrically safe, but the lockout, the invalid button push would no longer work. So the code, I expected the 2 button pushes horizontally to work, and I tested my code to make sure of that. And I said, I wonder what will happen when I press 2 this way. I expected to get a valid code. When pressing 4 and 7 together, I expected the code to return 4 because that's the first one it hits in the loop. But it returned -1. And so I had to think a little bit. Realized, oh, pin 4 is shorted to pin 7, A2 is shorted to A1. Both of those inputs are now right at the CMOS threshold. It probably doesn't work. And that's not a bug, it's a feature. So the process is to scan for a scan code, convert it to a key code, then draw the key number in this test case and test for the special control characters. In your case, what you're going to do is set this up as a callable thread, as a spawnable thread, or you could write it as a function, it doesn't matter. But you're going to return the key number rather than write it, although you might write it for testing. So the scan code is going to return a possible digit to a state machine, which is then going to determine whether at a higher level the push is valid or not. So at the low level, first of all, we have to make sure we have a valid button push. Now the next step is to make sure we have a stable button push, that when the user pushes it, it isn't still bouncing. You'll never see it bounce by eye, but the CPU is faster, and so it can see bounces. Is it clear how this works? Any questions on this? There's other ways to do it. There's much fancier ways to do this, including port direction switching and all kinds of interesting things. But this is pretty good. Works pretty well.
Well, I just had a quick question about the whole demounting thing. So we're doing that in software after we've determined what key was pressed?
Yes.
Or we just check again?
I'm going to draw the state machine in just a minute,
Okay, cool.
once we're all okay with this. Now, as I said in one other, last week sometime, these buttons can bounce. They do bounce. So instead of producing a nice edge when you push or release, that's a push, you instead get something that looks like this, where you might cross the CMOS threshold 2 or 3 times. And we want to reject crossing of the thresholds within a few milliseconds of each other, because no human can produce that. So it must be artifact. And as soon as I say no human can produce it, usually somebody holds up their hand and says, I can do it. Have any of you ever tried to see how fast you could push a push button twice in a row? How fast was it? Pardon me? Something like that, yeah. The tenth of a second sounds reasonable. What, you had another estimate? 10 to 12 a second. So again, that's like 80 milliseconds. So as a slight aside, there is a form of entertainment called quick draw, where you stand there, you pull your .357 heavy handgun, fire on target, put it back in your holster as fast as you can. You have to hit the target. The world record for doing this is 80 milliseconds, including cocking. And you watch the guy, what he's doing is this. He pulls it, hand comes across, he fans the hammer with the trigger pulled, right? Hits on target, gets it back in there. You can't see it. He's standing there, you hear bang, and he's still standing there. What the hell happened? They had, I mean, you have to see it. I mean, you can get it on YouTube. It's, look up, world champion quick draw. Guy does another trick. He hits 2 balloons about a radian apart. They're not too far away, probably 10 feet away, but they're this far apart, radian apart. Quick pulls a .357 out of the holster, hits both balloons, and puts it back in the holster in 100 milliseconds. How do you do that? Well, most people can't. In fact, I mean, he's got an unusual nervous system. So there are people that are quite fast, faster than you think. but most of you aren't going to push a button more than 10 times a second unless you practice for a few years. Doesn't seem like a good use of time.
That's what they said to the right brothers.
And a certain quick draw artist. So, thinking back to state machines now, the formalism I'm going to use is that on the tick, so we have to specify a delta t for the state machine, but on the time tick, so this is going to map into some sort of TRT wait and tell command. On the time tick, we're going to start with a state with some name and some test condition, and based on the test condition, we're either going to move to a new state. So this is the result of the test, and this is the action that has to occur as a result of the test. And then there's another action, another possible exit, which is another result and another action. And mostly what I'll draw are binary test state machines. So there'll be one of two actions and one of two paths that are taken. And the state transition is going to happen on the delta t, and every action is going to happen on a transition. So we're going to assume that there is a function called keypad, which returns the digits 0 through 9, pound, star, or -1. And we want to know when the press is valid and debounced. So what we're going to do is build a 4-state state machine. First state is going to be release, and the test is going to be key code equal -1. And we're going to enter this at reset. If the answer is if the answer is yes, we do nothing but call the function keypad. If the answer is no, we go to another state called maybe. We call keypad, but before we call keypad, we note the current value of keypad. So we're going to say that the pattern we're interested in, the pattern of key presses, in other words, the key code or the key number, the pattern we're interested in is equal to key code. And then we're going to call keypad again. Here, we're going to ask, is the new key code equal to pattern? If the answer is no, where do we go? Back. No, and we call keypad again. The answer is yes. The answer is yes. At this point, we know we have a valid key push. It's been pushed twice in a row at 30 millisecond intervals. We know we have a valid key press. So here, we're going to do whatever has to be done to this digit. Record a digit. or perhaps play a tone, for instance. And call keypad. So on this transition is where the action occurs once. And we're going to go to another state, still pushed. And we're going to ask, is key code equal to pattern? If the answer is yes, we're just going to hang here for another cycle and call keypad. If the answer is no, we're going to go to may be released and ask, is key code equal to pattern? If the answer is yes, we come back here. If we're not equal to pattern here, we go over here. So yes, no, call keypad. And if the answer is no here, then we know we're finally released, and we call keypad. So you're going to build a 4-state state machine. It's very safe. It's interlocked. Once you press and hold, then you have to unpress and not hold for 2 30-millisecond cycles before you can press again. So it's very safe in terms of producing bouncing multiple results on a single push. At the cost of a little bit of program complexity, but not much. Any questions on this?
Is there another keypad on the yes that goes back to state 3?
Thank you, yes.
On the arrow from the release to the first maybe, is that supposed to be a no?
Yes and yes. That would be bad. No. Thank you. I don't know where that came from. What else? So, the way you would normally code this in C is as a case statement in a thread, where the thread is going to execute every 30 milliseconds. It's going to, when it executes, it's going to spawn a keypad thread. That's interesting. Okay. It's going to spawn a keypad thread, get a new value back, and then run the state machine on it. So up in Lab 2, I wrote a state machine pseudocode for one button only. Can't do all the work for you. So this is for one button. This is to give you the template for how to write a state machine, not how to do this state machine, how to write a state machine. And it's very straightforward. We're going to define a thread. We're going to begin the thread. We're going to so this is pseudocode, folks. That means some port pin true when pushed. This is for one button. Undefined where the button is or anything else, but some button that defines the value of press as true when pushed. And there's going to be a state variable called push state that is going to be modified in this thread, but starts at reset time in the state no push. So this is initialized to no push. So if press is true, push state goes to maybe push. Push state, else push state goes to no push. Didn't really need to put that in, but orthogonality is important. Case memory, maybe push. If it's still pressed, the button is still pressed, there's only one button. Push state goes to push, and then more code to record a digit or start a tone or whatever other event you want. Else push state goes to no push. And remember, C requires a break between stanzas. Case pushed, push state goes to pushed, else push state goes to maybe no push. Case name maybe no push. If it's not pressed, if it is pressed, it goes back to pushed. If it's not pressed, it goes to no push. End of state machine. Really easy to code. You're going to have to change this to call the keypad, probably at the top of the. I mean, you could code it so it spawns a keypad event or a keypad press for every different one of these states, which is how I wrote the state machine. But it would make a lot more sense to just call keypad once right here. That way it will have a fresh push button state every time through the state machine, which will happen about every 30 milliseconds. It's about right for humans. You could tune it. You could make it a little slower, a little faster. If you find that 60 milliseconds feels laggy, you could drop it to 20 milliseconds or 15 milliseconds. But don't drop it much below 10 milliseconds because you'll start getting into the bounce regime of the keypad itself. Questions? In your state machine, first of all, you're going to have to be looking for a pattern of buttons rather than a single button. And depending on which button is pushed, you're going to have to do different stuff here. For instance, if a number button is pushed, you're going to have to play the DTMF tones. If the star button is pushed, I can't remember which is which now. Star button is pushed, you erase, and if the pound button is pushed, you play the number. I think it's the way it is. You're going to have to play the whole, you're going to have to dump the state of the system into the audio. So this piece of code, this piece of the state machine might be a little large, or it might be a separate function that you call. Yes?
Why not do those state switching when you're actually reading from the pins and then just pull that figure, and then have another for doing your actual logic?
So you can arrange this any way you want. I happen to like to factor it into a low-level scanner, which does all the weird I/O bit twiddling to get a number out, and then a state machine that works on the abstract digit number without having to worry about the hardware. But it's up to you. You can mix them together if you want. So at this point, you have enough information to start Lab 2. And you should, because Lab 2 is a 2-week lab. For the Tuesday people, the second lab starts today. This is the first day of the 2-week lab. For the Wednesday people, Lab 2 starts tomorrow. Don't wait till your first scheduled lab a week from now to start lab 2. Start it now. Yes. I got a bucket of speakers. I have a couple of dozen of Logitech's cheapest speakers. So the tonal quality is not wonderful, but it doesn't need to be for this particular exercise. It doesn't do low frequencies well at all. They're little tiny speakers. But they're close to indestructible. Except somebody has managed how to pull the volume control knobs out of them. I shouldn't have even said that. I wonder how that works. Yeah. Yeah. They are amplified speakers. So you can put a so-called line level signal into them, plus or minus 1 volt at a few hundred ohms or a few thousand ohms impedance, and it will work. So it draws almost no current. They are capacitor, they are high pass coupled to their input, so you don't even have to get rid of the DC level, because it does it internally in the amplifier. Well, although one of the homework questions is, would it be a good idea to use a low pass filter? You might think about that. Any questions? It is an MSP 8422, something like that. It's an SPI 2-channel DAC. 2-channel DAC. Oh, you could put out it's dual tone. You could put out 1 tone on each channel. Or you could just add them together and put them out on 1 channel. Be easier to test that way, actually. Next topic, just to warm your brains up on this. Next topic is direct digital synthesis, whereby we are going to think about the relationship between register overflow and phasers. The primary abstraction being to calculate a sine and cheap chalk. To calculate a sine and cosine from a you typically think of a sine wave signal as being the result of some sort of rotating process, right? Typically a phasor, which is rotating at a fixed angular velocity, some omega angular velocity, which results in a certain frequency of output. So we start at 0 degrees, we go to 360, we overflow back to 0. That is exactly the same topology as having a n-bit register that you increment on the clock until it overflows back to 0. So we're going to define a scheme for generating a sine wave based on 1 cycle per register overflow, which will be directly related to 1 cycle per phasor overflow back to 0. That's just a teaser for the next lecture. Any last questions? Thank you.